So hello everyone and welcome. This is the next lecture. I've lost track of exactly how many, although the slide says lecture 9 in the STEG online course on key concepts in macroeconomic development. I'm Doug Gollin. I'm one of the academic leads with Joe Kaboski, and I want to welcome everyone who's joining us for the lecture. We're really delighted to have Ben Moll today talking about heterogeneous agent models and their applications in thinking about structural transformation. Let me just start off by giving a few thank yous, a few disclaimers, and a few ground rules. The thank yous, as always, we are grateful to the United Kingdom's Foreign, Commonwealth and Development Office, which funds the STEG program, and which has made it possible for us to organize and run this course. I also want to thank colleagues at CEPR in London, especially Mandy Chan, who's been emailing all of you, and Kirsty McNeil and Lauren Waring, and actually a bunch of other people working in the background so that this online course runs as smoothly as it does. And I especially want to thank Ben, who, like the other lecturers on this course, has made his time and knowledge and expertise available, and really out of the generosity of his heart. For those of you joining, the slides for today's lecture are posted online, and we'll have if you haven't already downloaded them, you should feel free to, along with other materials from this lecture and previous lectures. Also, the lectures are all available on YouTube after the fact, and they're live streamed on YouTube as well as this. And so please do find your way to the slides. In terms of ground rules, what you'll find are those of you who are in the virtual front row will have access and control over your microphones and cameras. Please do leave your cameras on if you're willing, because it gives Ben a chance to feel that he's speaking to real people. Ben's going to talk for about an hour and a quarter. If you've got questions in the front row, please, if you can, leave those to the end. He'll pause a couple of times along the way. And so if you have clarifying questions at those pauses, you can ask them then. But he'd prefer not to be interrupted in the train of the lecture. So if you can just hang on until he invites some questions, that will give him a chance to manage his time effectively. For those of you who are watching on the webinar portion and who won't have control over your microphones, please do enter questions in the Q&A window, which you do have access to. And one or another of us will try to answer those questions ourselves, or we'll hold them. The really tough ones we'll hold and pass along to Ben at the end. So on that note, and without further ado, I'd just like to say, please welcome Ben Moll from the LSE and CEPR, and Ben, over to you.
Fantastic. Thanks so much, Doug, and thanks very much, everyone, for coming. Let me share here. Okay, so I mean, as the title says, I'm going to talk about heterogeneous agent models and methods. So just to motivate this a little bit, I want to come back to the introduction lecture that Richard Roderson gave to this course, where he had this nice slide here on the role of frictions and heterogeneity in macro. And essentially, what today's lecture is about is exactly that. And what Richard said here, right, is that the major focus of macro over the last 20 years has been the development of models that incorporate rich specifications of heterogeneity and frictions that can simultaneously speak to aggregate outcomes, while also, I think someone has their mic open. Can we mute everyone? While also addressing a rich set of cross-sectional effects. And then here comes the key part, with vis-a-vis this course here. So these models present an opportunity for unified analysis of micro and macro development within the same framework. So that's really, the angle or the perspective we want to push here. And in particular, you've already seen Paco and Joe and Rob have this nice sort of agenda setting paper that talks about this. And I kind of want to teach you the tools to be able to do this type of work. Okay. Put differently, so my goal here is enable you to work with models like the ones in these papers here. So I've already said this agenda setting paper here. There's also this handbook chapter by Banerjee and Duflo. I'll give you an excerpt from there. And then here's some sort of specific papers. And there's a brand new paper here by Diego Cavalcanti, Joe, and others that just came back out as an NBR working paper. I'll talk about that a bit. And then here, two other papers. So Bora and Shen is sort of a well-known macro development paper. And then this is to tie in with yesterday, I think's lecture by Mushfik. So if you want to think about migration and risk, these kind of models are obviously useful as well. Okay, here's an excerpt from this Banerjee and Duflo handbook chapter, so growth theory through the lens of development economics, that some of you may have seen. And they have this nice section there, which is entitled Towards a Non-Aggregative Growth Theory. And I'm not going to, read the whole thing to you, but essentially in this section, they spell out here, they say, the question about how an economy works under the assumption that the only source of inefficiency here comes from limited access to credit. And then the goal is to illustrate what non-aggregative growth theory might look like if you have heterogeneity and limited access to credit. Okay, and they spell out a model, and there's some preferences there, for example, and there's some technology there. And one of the technologies they like to focus on is what they call sort of S-shaped technologies. So technologies, for example, if you have fixed costs, or another way of saying this is where there's some non-convexities in production. Okay, and then they have a nice verbal discussion of like what happens in these kind of models, and they have some discussion about under what circumstances do people get stuck in a poverty trap and so on, and is this fragile or not with respect to the introduction of random shocks and so on. Okay, now I don't want to get too much into this, but the points I want to make here is, first of all, this sort of non-aggregative growth theory, that's the word they use, but what that really is exactly heterogeneous agent macro of the type I'm going to talk about. And then the other thing I want to do is, say is that this handbook chapter has this very nice and interesting sort of speculative and verbal discussion. But what I want to do is I want to kind of move beyond that. I instead want to teach you how to actually solve and analyze such models. And for me, one primary motivation is that I, for one, am at least not smart enough to figure out how these kind of models work without actually solving them. Okay, Abhijit and Esther, see, this is actually all correct. I think what's in the handbook chapter, they're smart enough to do this all verbally. I'm not, so I want to teach you how to do this with on a computer and with equations. Okay, here's another thing I want to briefly talk about, which is this recent paper by Tiago, Joe, and others. Read through the abstract. This is some very nice application of this sort of micro to macro development approach. They have this very nice Brazilian data, and they document some nice facts there about dispersion and credit spreads, and then they put that into a model of firm dynamics with entrepreneurship. There's like an occupational choice and so on. And I'll talk about this type of model a little bit at the end. What I want to highlight is two things. So this paper uses exactly the type of methods I'll teach you today. And then the other thing that's cool is Tiago, Joe, Bruno, and Cesar were kind enough to actually share their codes. They're up here on my website, so you can actually play around with this code yourself. So you can actually take the codes from this paper that's sort of a fully completed working paper and see how you would actually apply these kind of methods to a really exciting and interesting question there about macro development. Okay, so here's my outline. I'm very briefly going to talk about discrete time heterogeneous agent models. Then for the most part of my lecture, I'm going to talk about continuous time methods. I'll motivate why I think this is useful a bit. I'll give you a crash course, if people haven't seen this, on continuous time Bellman equations. I'll talk about sort of the textbook heterogeneous agent model, so an Iagari model essentially, and then I'll talk about numerical solution. And then in the end, if there's time, I'll talk about these types of problems with non-convexities. So in particular, capital accumulation with these kind of S-shaped production functions that Abhijit and Esther talked about in this handbook chapter, and occupational choice, like in this paper by Tiago and Joe and others that I talked about. If you look at my slides, I have like 50 or 60 slides, I forget. You'll see it's way too much material for the 75 minutes that I have. As a result, I'll skip a lot of the slides. In particular, there's some slides that say skip in red on top, and those are the ones I'm going to skip. Okay. Here's just a list of references. This is just for completeness. the things that I haven't mentioned yet. A lot of the methods I'll draw on is from this paper of ours here. And in particular, I have this website with codes up here. And one set of codes that will be particularly relevant is sort of a continuous time version here of this Warren Chin paper from 2013. And there's some notes and codes here. This one is something I'm not going to have time to talk about, but this is just something, in case it hasn't been talked about in this course, that I think everyone should be aware of who does this sort of micro to macro work, which is something that's called a missing intercept problem, which is if you try to go from cross-sectional data to aggregates to macro stuff, there's a problem that occurs. And there's surprisingly many people who aren't aware of this, in particular, sort of sometimes applied microtypes get this wrong. And I think it's sort of something everyone should be aware of. So check this out. This is sort of separate. Okay, on Monday, there's going to be a TA session with Kotya, who's here on the Zoom call as well. Here's the date and time. The point of the TA session will be to essentially get your hands dirty and go through the codes, okay? And then Kotya will also answer any outstanding questions you may have. Okay, now just briefly, I said I'm going to do this in continuous time. However, if this is, especially if this is sort of your first encounter with heterogeneous agent models, I think especially for pedagogical reasons, you may want to first learn this in discrete time. And now, because I wanted to bring you up to the frontier, I decided to teach this in continuous time. But if this is all a little bit overwhelming, you may want to look at these other lecture notes here. These are my first year LSE PhD lecture notes, where it's all in discrete time. And there's also a set of codes in all of MATLAB, Python, and Julia to solve these kind of models. Those were originally written by my buddy Greg Kaplan, and then a student of mine translated them into Python and Julia. And there's also some other computational resources. And maybe this is useful even if you don't like these or are not going to end up using these continuous time methods. Okay, so now let me jump into the main meat of the lecture today, and in particular, essentially continuous time methods for solving heterogeneous agent models. I want to motivate very briefly and sell you a bit on what are the advantages of doing these things in continuous time. Okay, here's essentially 4 concrete advantages I could think of that arise when you numerically solve a heterogeneous agent model in continuous time rather than discrete time. Okay, the first thing is the first 2 things are something about first order conditions. The first one is something about handling Boring constraints. And the third and fourth things are essentially about speed gains you have when you write these things in continuous time. Okay, so let me just go through these kind of briefly. The first one here is one thing that's nice in continuous time is that you never have to worry about these sort of occasionally binding constraints and that you may have seen come up in discrete time models. In particular, Boring constraints of the type that you'll have in a typical heterogeneous agent models always only show up in boundary conditions of some partial differential equations essentially that you're going to solve. So the first order conditions are essentially always going to hold with equality everywhere in the interior of the state space. The intuition here is that because time is continuous and the typical state variables we work with, like wealth and capital, move continuously, then if you're strictly away from the Boring constraint, then in an infinitesimal amount of time, you're not going to hit the Boring constraint immediately, okay? And so then the Boring constraint is only essentially going to bind if you're kind of already there, okay? The second thing is something that's related, which is that first order conditions are much easier to handle. In particular, first order conditions end up being sort of static and you can typically compute them by hand. In contrast, in discrete time models, you're going to have to use a root finding method typically to solve a first order condition. The intuition is essentially that in discrete time, you're going to have a first order condition, which is going to be something like, marginal utility of consumption today equals beta times marginal value of wealth tomorrow, okay? And then wealth tomorrow depends on your consumption decision today. In continuous time, there is no tomorrow and today. And instead, there is sort of tomorrow is today, right? And instead, what you have is marginal utility of consumption equals marginal value of wealth today, not tomorrow. And then given a guess for the value function, this is just a number, and you can essentially solve a first order condition by hand by just inverting this here. Third, sparsity. So essentially, the way this is going to work when you solve a Bellman equation in particular is you're going to iterate somehow. It's going to be very similar to sort of value function iteration. Okay, and in particular, at each step, you're going to invert some sort of a matrix, which is also something you do in discrete time typically. However, what's going to happen is that these matrices are going to end up being very sparse. So meaning they have lots of zeros. Okay, in particular, they're going to be something that's called tridiagonal. Here's the intuition. So essentially, these matrices are going to be kind of transition matrices of how you move in the state space. Okay, and then the idea is once you discretize a continuous time process, you're essentially going to end up with what's called a tridiagonal matrix, meaning a matrix where it has only non-zero entries on the diagonal and one to the right and one to the left. What's the intuition? The intuition is if you discretize a continuously moving process, you're only going to move locally. Okay, so you're essentially what you're going to do is you're either going to stay where you are, or you're going to go one step to the left or one step to the right. Okay, you're never going to go 6 steps to the right or 7 steps to the left. Okay, and because of that, all these sort of further off diagonal entries, you know, the 7th next to the main diagonal are going to be zeros, and you're going to have a lot of sparsity. Now, the good thing about this is when you solve linear systems or you invert matrices that have a sparse structure, there's very good numerical solvers for doing this, and you get massive speed gains. Finally, there's something that I call here 2 birds with 1 stone, which is when you solve these models, you're essentially going to solve a continuous time Bellman equation, and you're going to solve what's called a Kolmogorov equation, which is an equation for the stationary distribution. What's going to happen is that essentially, once you solve the Bellman equation, you're going to kind of be able to solve the distribution in one step, and essentially with just 3 lines of code or something like this. And the intuition is that there's also going to be a transition matrix in the equation for the distribution, so the Kolmogorov equation. And this equation for the distribution, this matrix in the equation for the distribution is just going to end up being the transpose of the transition matrix for the discretized Hamilton-Jacobi-Bellman equation. Okay, and there's sort of a deep underlying mathematical reason that we can get into later. But the point here is that essentially you kind of get 2 birds with 1 stone here, because once you've solved the Bellman equation, you kind of get the distribution for free, essentially. Okay. Now, one thing I want to just briefly emphasize, this is essentially the advantages if you solve a standard heterogeneous agent model like an Ayagari model. Now, if you're a smart enough programmer and you know your little tricks in discrete time, you're going to be able to solve especially a stationary equilibrium, say, of a heterogeneous agent model pretty quickly in a few seconds. Okay, I'm going to be able to do it in like, I don't know, a quarter of a second maybe. You're going to be able to do it in 5 seconds. Okay, it's not going to make that much difference in practice. Okay, however, once you go to more complicated setups, then this is going to really pay off. Okay, in particular, once you have non-convexities, meaning in particular these S-shaped production functions or occupational choice, then these continuous time methods are really going to dominate the discrete time ones. Similarly, stopping time problems, so optimal exit decisions or something like this. Once you have more than 2 state variables, so say you have portfolio choice problems, or you want to do transition dynamics or aggregate shocks, so more complicated problems, then these continuous time methods are really going to pay off. Okay, now let me pause here very briefly and see if there's any questions before I go into the sort of more technical stuff. No? Okay, then I'll continue. Okay, so I'm going to do sort of a crash course on continuous time Bellman equations, and then again I'm going to tell you later how to solve them on a computer. But just in case you haven't seen this before, I can't tell you how to solve an equation that you've never seen, so I need to tell you first what the equations look like. Okay, I'm going to skip the next 2 slides These are just even more basic, a reminder of how discrete time Bellman equations work, okay? And they're in particular meant to show you the analogy to the general notation I use when I introduce the continuous time Bellman equations, which I'm going to do now, okay? So here's how this is going to work. So the idea is going to be that pretty much all deterministic optimal control problems, so say a consumption saving decision, capital accumulation, and so on, when you write them in continuous time, can be written in this general notation, okay? And I'm then going to essentially on the next slide show you how to write the sort of corresponding continuous time Bellman equation. So here's the general setup. The general setup is there's some vector of state variables x, okay, and for now this can be an n-dimensional vector. There's some other vector of control variables alpha, okay, and there's going to be what's called the instantaneous return function r, and there's a law of motion of the state f, okay. Essentially the setup here is going to be that you're going to want to maximize the present discounted value of utility, of this period return function, subject to the state vector evolving according to this law of motion here. Okay, now this is all a bit abstract, so let me give you a specific example. A specific example that hopefully most of you will be familiar with from your first year PhD course is the neoclassical growth model, okay? Or more generally, just, you know, some capital accumulation problem at the individual level. So then the question is, how do you map, you know, this problem into this more general problem, okay? Essentially, the way this is going to work here in the neoclassical growth model, what's the state? X, so that's the capital stock here. What's the control? What I called alpha on the previous slide, well, that's consumption. And then what's the law of motion of the state? Well, that's just the resource constraint of the economy, right? Which is, you know, output minus depreciation minus consumption is the change in capital, okay? And so the point is, what I want you to think is whenever you have a particular optimization problem that you want to solve, you want to be able to map it into this more general problem, okay? You want to be able to say, okay, wait, this is my state variable, this is my control variable, and then you have it formulated in the more general problem. And then the point is, on the next slide, I'm going to tell you how to write, and then later solve the Bellman equation for the more general problem. So that's going to give you the toolbox to essentially solve any sort of optimization problem you're going to want. Okay. So I can see there were some things in the Q&A box. By the way, I can't see what's in the Q&A box. I just see like a thing popping up. But I'll take questions maybe in like 3-4 slides, and then you can ask these questions hopefully. Okay, so here's the crash course for continuous time Bellman equations. So the question is, how do we analyze these type of optimal control problems? Okay, and I'm just going to essentially use here what I like to call the cookbook approach. Okay, I'm just going to tell you a recipe for how to do it. Okay, I'm not going to tell you at all how the recipe works and why. Okay, so it's exactly like, you know, cooking according to a cookbook. You just switch off your brain and you follow the recipe, and you don't question the recipe. So this is how we're going to do it. Okay, so here's the recipe. So the recipe is, if you have a generic optimal control problem like this, then the value function of that generic optimal control problem, so the function v from 2 slides ago, is going to satisfy a continuous time Bellman equation, or Hamilton-Jacobi Bellman equation, which looks like this. Okay, so let me read through this. So it says the discount rate, so rho, right? So you remember rho was like the discount rate here, times the value function is equal to, then there's a max over the control of the period return, plus then there's the derivative of the value function times the law of motion of the state, so f of x comma alpha. Okay, the point here is, and so let me maybe not skip this entirely, this is exactly analogous to what a discrete time Bellman equation would look like, which you're probably more familiar with, except that it's in discrete in continuous time. Now, if you've never seen this, what's a little bit tricky is like, wait, why is there a row here? And why is there a derivative here? And I'm not going to explain this to you, okay? You're just going to have to take me at face value. That's the whole point of the cookbook approach. That's just how it is, okay? I'm kind of kidding. There's a derivation on the next slide for the neoclassical growth model, but I'm not going to go through that, and you can do this in your free time, okay? The point is, it's always going to have that same structure. So discount rate times the value function is there's a period return, and there's the derivative of the value function and the law of motion of the state. So x dot here, the time derivative. Okay, so here, let me apply this to the neoclassical growth model, right? This cookbook approach. So then what this is just saying is, in the neoclassical growth model, once you follow the cookbook, you can immediately see that the Hamilton-Jacobi-Bellman equation for the neoclassical growth model has to look like this, right? It's rho times the value function. Now the state is capital, then the control is consumption, then it's the derivative of the state, and this is k dot, so the law of motion of the state, okay? And then you can continue by taking first order conditions and so on. What's useful and maybe instructive and helpful later is to compare this to what this would look like in discrete time, okay? In particular, here's something I said in the introduction. There's an interesting difference between the first order conditions. In continuous time, in discrete time, the first order condition is marginal utility of consumption equals discount factor times marginal value of capital tomorrow, so k prime. In continuous time, instead, it's a simpler condition. So it's marginal utility of consumption equals marginal value of capital today, not tomorrow. And that's where a lot of the simplification is going to come from, okay? Okay, so here's this derivation of this continuous time Bellman equation, which I'm going to skip, and you can do it in your free time. Okay. Now, let me do one more thing and then pause for questions, which is what I did so far was for the deterministic case, so meaning no uncertainty. Turns out it's quite easy to extend this to uncertainty. A particularly easy and nice case of uncertainty to work with in continuous time, it's what's called a Poisson process. And the easiest one of those is just a two-state Poisson process. This is just the analog of a discrete time two-state Markov chain, right? Your income or your state switches between two values with some probabilities. Here's an example that's easy in this context, which would be, rather than having a neoclassical growth model, let's do a real business cycle model, meaning just a neoclassical growth model, but with productivity shocks, okay? And then let's assume that this productivity process here follows a two-state Poisson process. So at some rate lambda 1, you switch from Z1, say low productivity, to Z2, say high productivity, and some rate lambda 2, you switch back, okay? Now it turns out, and this is again just cookbook, I'm going to assert this, the Hamilton-Jacobi-Bellman equation for this approach looks exactly the same as before in terms of the initial terms, except you chuck on this extra term here, okay? What's this extra term here? It has a simple intuition. This extra term here is just at rate, say you're in state 1, right? So then so I equals 1. And then at rate lambda 1, you switch to rate 2, and then you get a gain in the value, say, of V2 minus V1. Say if Z2 is bigger than Z1, you get a gain in the value. And conversely, if you're in state 2, and then you're going to, at rate lambda 2, switch to state 1, and then you're going to get a loss in the value, okay? And then everything else is kind of the same. Okay, so let me pause here and take some questions. And I realize I'm going fast, so please interrupt me if anything's unclear. Just unmute yourself and ask the questions. Were there any questions from you, Doug? No?
There's one from Xiaomei Sui. I think this just comes from, I'm not exactly sure what he's.
You're muted.
Sorry. From Xiaomei Sui is, was expecting to see a partial derivative of the value function with respect to time. So why is, you take time t to the limit 0, he was trying, why is there, he's basically asking why is there no partial derivative with respect to time in the Hamilton-Jacobi-Bellman equation?
It's because it's a stationary problem.
Yeah.
So, right, in the same way in a discrete time Bellman equation, if you have a stationary problem where nothing in the environment changes over time, then you eliminate time from the problem. That's in a sense the whole point of recursive notation, right? Is that you get rid of calendar time and you instead write everything on the state space. Okay, we're doing the same thing here in continuous time, and you can do that whenever the problem is stationary. Later on, we're sometimes going to have problems where there are going to be partial derivatives with respect to time. In particular, when we do heterogeneous agent models and we do transition dynamics in the heterogeneous agent models, then the prices are going to change over time. So then something in the environment of the agents is going to change over time. And then the value functions are going to depend on calendar time because the prices do. And then you're going to have partial derivatives with respect to time showing up. But for now, this is just a stationary neoclassical growth model or RBC model. And then nothing depends on calendar time. Everything is recursive.
And Kuldeep Singh asks about the boundary conditions associated with the HJB.
Yeah, there's a discussion in 2 slides that I'm not gonna have time to talk about. The whole point though, wait, I have it here, here. I even have it here. Let me flash it by very briefly. There's sort of a math 101 way of thinking about differential equations here, or in particular these Hamilton-Jacobi-Bellman equations, which is, oh, wait a minute, this is a first order ordinary differential equation, so I need a boundary condition to solve it. The whole point is going to be that here, this is not the right way to think about it, okay? In particular, these are not just any ODEs, these are Hamilton-Jacobi-Bellman equations that come from an optimization problem. And in the same way, you don't need a boundary condition to solve a discrete time Bellman equation. You're also not going to, in general, need a boundary condition to solve a continuous time Bellman equation, except if there's borrowing constraints in these kind of things. But in the neoclassical growth model or an RBC model, there are no borrowing constraints. So then you're not going to need a boundary condition. But it's something I don't have time to go into. Other questions? Okay, so let me go on. So yeah, there's some more general thoughts about what's the right way to think about these Hamilton-Jacobi-Bellman equations. And there's something about viscosity solutions. This is kind of a little bit too advanced probably, but if you're curious about these kind of questions and exactly do you need boundary conditions or not, then do read these slides and there's some discussion there. Okay, so this was my crash course on continuous time Bellman equations. I'm quite happy. I managed to do this in like 10, 15 minutes, I guess. Okay, so now that we have that out of the way, we can move on to a heterogeneous agent model, essentially. So the way I'm going to do it here is I'm going to try to write down the simplest possible heterogeneous agent model I could think of purely for pedagogical reasons. It's essentially going to be a Huggett model for people who know this with a 2-state income process. Okay, just high and low, like employed and unemployed. Okay, and the point is I'm going to do all the slides and equations for that particular setup. And the point is everything is going to generalize to much more complicated setups. For example, more complicated income processes, other ways of closing the model. So like an Iagari model where you have the asset being productive capital rather than, bonds like in a Huggett model. Or if you have, more than one asset, everything's kind of going to look the same. But this is sort of the most minimal and most pedagogical setup to explain to you how the things work, essentially. Okay, so here it is. So there's a continuum of households. This is the standard assumption in these heterogeneous agent models. So each guy is atomistic. And these households are heterogeneous in their wealth, A, and their income, Y. And then so those are going to be the 2 state variables, and there's going to be a cross-sectional distribution over those variables, wealth and income. And then each guy, given his or her state variable, is going to solve this kind of a problem here. Okay, So essentially, maximize the expected present discounted value of utility from consumption. So same objective as before, subject to a law of motion for their wealth. So this constraint here just says a person's savings, so A dot, so the time derivative of A, of its wealth, is equal to your labor income plus your interest income minus consumption. Okay. Note here also, this is going to be the equations for stationary equilibrium, so that's why R is not going to have a time subscript. R is just going to be a number. Okay. The income process here, as I've already said, is just a two-state process. So it fluctuates between Y1 and Y2 with some Poisson intensities, lambda 1 and lambda 2. So if you want for concreteness, and that's an interpretation I like, think of Y1 as the low state and Y2 as the high state, and you can think of maybe state 1 as being unemployment and state 2 as being employment, and then lambda 1 is the job finding rate and lambda 2 is the job loss rate. Okay. So there's your consumption that you choose that determines how much you save. Your income, moves around stochastically in the background. Sometimes you get unlucky, sometimes you get unlucky, and you try to maximize this. And then you also face a borrowing constraint. Okay, there's a constraint which says your wealth A has to be greater or equal to some number A lower bar, so your wealth cannot go to negative. The simplest possible case, or also the most extreme case, would be A lower bar equals 0. That would say that you cannot borrow at all. Okay. So a strict no borrowing constraint. More generally, you could have some other constraint there. A has to be larger than, say, minus $10,000. That means you can only make $10,000 in debt. Okay, so that's the setup. Okay, and what you want to start thinking about already is, what are the consumption and saving decisions of these guys are going to look like. They're going to be hit by these idiosyncratic income shocks, and they're going to try to smooth consumption in return, and they're going to maybe try to accumulate some assets as a buffer stock against this and these kind of things. I'll talk about this in a second. Okay. I've already said this. Here it's a two-state Poisson process. This is purely for simplicity. You can do something much more general. For example, a continuum of income states, diffusion process, jump diffusion, doesn't really matter. The whole methodology is going to be the same, essentially, whether it's this simple process or something more complicated. Okay. Equilibrium here, just for simplicity, I'm going to assume that the equilibrium condition is that the bonds in this economy, so the A here, is in fixed supply. So for example, you could have the case where the bonds are in zero net supply in the economy, meaning that for every person who borrows, there's someone else who saves, and all the A's have to sum to zero. Okay, that would be exactly a Huggett model. More generally, you could have a non-zero fixed supply. There's also other ways of closing the models. For example, as in an Ayagari model, you could have that this asset here is productive capital. That's a little bit more complicated, but once you understand the Huggett model, it's all going to be kind of the same. Okay, the partial equilibrium problem of the households is going to be the same. Okay. Now let's think briefly what the policy functions here are going to look like, and also what the distribution is going to look like in a stationary equilibrium. Okay, these are in fact going to be graphs that are generated using the numerical algorithm that I'm going to show you later. Okay, but because the number, because I didn't calibrate it in any way, I took off all the quantities from the axes because they wouldn't mean anything anyway. Okay, so let's think just about the qualitative properties of this type of model. Okay, so here's a consumption policy function, here's a saving policy function, and next slide I'll show you the stationary distributions. Okay, so this is consumption as a function of wealth here, and then remember I said state 1, let's make income state 1 the low income state, so the blue line is consumption of low income guys, and state 2 here is consumption of high income guys. Okay, so consumption here you'll see there has a bunch of property that are not particularly shocking. First of all, consumption is increasing in wealth. The wealthier you are, the more you consume. And second, the more income you have, the more you consume. So, you know, the red line is above the blue line. Okay, so that should hopefully kind of make sense. Over here is saving. Okay, what's this in particular? Optimal saving here is the optimally chosen A dot. Okay, so it's this thing here where consumption is the optimally chosen consumption policy function. Now, if you're used to looking at discrete time models where you have sort of AT plus 1, what this is here essentially is AT plus 1 minus AT. Okay, so it's like if you're used to looking at plots where there's wealth on the x-axis and wealth next period on the y-axis, then what you should do is essentially subtract off the 45-degree line and sort of think about the change in assets here. So in particular, this line here, the dashed line is 0. And so whenever the saving here is positive, people are accumulating assets. And whenever the lines here are negative, so down here, people are decumulating assets. Okay, so now what can you see here? So the first thing you see is that high income guys, so employed guys, say are you know, saving more than low income guys. So that kind of makes sense. And the other things you're going to see here are as follows. So first of all, this is the borrowing constraint. So savings here are 0 for the low income guy at the borrowing constraint. That kind of makes sense. So it cannot be negative because otherwise the borrowing constraint would be violated, right? This is A dot, right? So A dot cannot be negative at a lower bar. That's sort of the definition of the borrowing constraint. And the other thing you see is that over here, the red line is sort of positive for low wealth, and it kind of you know, crosses 0 at some point over there. Okay, so now with this in mind, what I want you to think about is how someone may evolve in the state space given some particular realizations of the income process. Okay, and remember, the blue line here is the saving policy function of the unemployed guys, so the low income types, and the red line here is the saving policy function of the high income types. Okay, so think about someone who starts their career, say, with wealth right about here and has the low income type. Okay, what's that person going to do? She's going to decumulate savings, right, according to that, decumulate wealth according to that policy function right here, because the blue line is negative. Remember, this is 0 here. Now, this guy is going to cruise towards his or her borrowing constraint. Then at some point, suppose that guy gets lucky and finds a job. Okay, what's that guy going to do? Well, he's now going to start accumulating savings according to this policy function up here. Okay, he's going to do that while he has a job, and he's going to kind of cruise according to that policy function until at some point maybe he loses a job again. What happens then? Well, you switch back to that policy function here and start decumulating assets again. Okay. And you can see that for particular realizations of the income process, people are sort of going to churn around in the state space according to these two policy functions. Now, one thing you can also see is that, okay, no one ever violates the boundary conditions, so the borrowing constraint, so that sort of makes sense, I guess. You can also see that no one is, so this red line here, I don't know if it's kind of cut off, but this red line crosses 0 at some point, okay? You can also see that no one's ever going to go beyond the point of wealth where the red line crosses 0. Why? Because if you're ever above that point, then both in the low income and the high income state, you would decumulate assets. So then in a stationary equilibrium, no one would be there, okay? So you can already see the support of, there is going to be a stationary distribution, a non-degenerate one, and the support of the stationary distribution is going to be a lower bar to wherever that red line crosses 0. Okay. Now, with this in mind, let's look at the densities, so the stationary distributions. So what you have here is what the distributions look like that come out of this. The way I'm plotting it is G1 is sort of the marginal distribution of income type 1. Conditional so the marginal distribution of wealth conditional and income type 1, sorry, and G2 here, the red thing, is the marginal distribution of wealth of the high income type. Okay, so what you get, not surprisingly given this, what you get is that the distribution of the high income types is further to the right than the distribution of the low income types, okay? Because these guys accumulate more savings. By the way, sorry, I should have said this. What's this called? The fact that the red line is positive, so that the fact that, you know, high income guys accumulate savings, that's called precautionary savings, okay? That's like the entire point here. So if you have a high income realization, what you do, you accumulate a buffer stock of saving. Why? Exactly because you want to be able to buffer low income realizations, okay? So that's the entire point here. This is a model of precautionary savings. Okay. The other thing you can see here is that there's a point mass of people here. In particular, it's going to be a Dirac point mass of people at the Boron constraint. Where's that going to come from? There's sort of a more technical reason, which is going to come from the fact that the saving policy function here has a lot of curvature. But intuitively, the way it works is that because of the setup of the model, people are going to hit the Boron constraint in finite time if they have a long enough sequence of low income realizations. So if you're unemployed for a sufficiently long time period, you're going to hit the Boron constraint in finite time. And then because of that, you have a buildup of people at the Boron constraint. Okay. So let me briefly pause here. And, you know, this is just so you have a little bit of an intuition for this kind of a model, how this kind of model works. A discrete time heterogeneous agent model here, by the way, works exactly the same. So, you know, let me pause here briefly and see whether this was sort of clear. I realize I'm kind of going fast, but, you know, does it make sense how I explained this model and what the properties are, the qualitative properties of this model? Any questions? Again, please.
Actually, I have a quick question. So, I mean, this distribution is fixed over time, right?
Mm-hmm.
If you have aggregate uncertainty, this is going to change?
Yes. Yes. Yeah. This is right now. I'm doing what usually is the starting point in the heterogeneous agent literature, right? Which is to look for stationary distribution. This here is the stationary distribution of the model. The reason why there is right, so you're looking for a distribution such that if you start with this distribution, the distribution replicates itself over time. So sort of if you start there, you stay there. It's sort of the natural generalization of a steady state. If you had aggregate uncertainty, or not even if you have aggregate uncertainty, just if you had something changing in the aggregate environment, then also the distribution would change over time. And then you'd have to think about transition dynamics or solving the model with aggregate uncertainty. And then, yeah.
So is it something like MIT shock you're referring to?
Yeah, or like even just deterministic transition dynamics, right? You're, say, here's an example. Suppose you're in an initial steady state, and then, you know, credit markets get better, and so a lower bar gets more negative, so people can borrow more. That would trigger some transition dynamics. Or, you know, maybe the job finding rate increases over time or decreases over time. And then that would trigger deterministic transition dynamics. Okay. Any other questions? But the point is, all of these things you can handle with a slight generalization of this type of method. It's just that for now, I want to keep it simple and focus on the stationary equilibrium.
Yeah, if I could ask,
yes.
Regarding the distribution, so there is just one Dirac point at the borrowing constraint, because in first year we solved Haggett model, and even with many states discretization of the income process, when I plotted the distribution, it looked that there are quite many Dirac points.
Yes, no, that's exactly right, and that's because you did it in discrete time, but we do it in continuous time. And the reason for it, it's like this: in discrete time, once you have a Dirac point mass at the Boron constraint, you can see that you're necessarily going to have a Dirac point mass at other points in the state space. Why? Because it gets fed by the Dirac point mass on the Boron constraint. In particular, everyone who is at the Boron constraint for a given income point realization is going to jump to exactly the same point in the state space next period. Right? The policy function takes you to the same point. So then, if you have a Dirac point mass at the Boron constraint, you're also going to have one at, like, you know, a lower bar plus 10, I guess. But then if you have one at a lower bar plus 10, you're also going to have one at a lower bar plus 20, and so on. And you get these Dirac point masses feeding through the thing here. In continuous time, that's not going to be the case. Why? Because you move away from the boring constraint in a smooth, continuous fashion. So and it's actually quite convenient because the only Dirac point mass you have to worry about is this one here at the constraint.
Yeah, so if I want to approximate the density function in a spirit of Algan and then Han, I could just handle it by kind of boundary condition.
Yes. Yes.
Okay, thank you.
So let me move on because otherwise I'm going to run out of time. Okay, so here are the equations, and I'm kind of going to go fast because they're going to look, well, at least the first one should be hopefully look familiar. Okay, so this is, so how, so now, now we've explained, intuitively how this works. Next, let me tell you just, what the equations are that you need to solve to characterize or numerically solve for this stationary equilibrium here, okay? This is a Hamilton-Jacobi-Bellman equation for the optimal consumption saving decisions. Again, what did I do here? I just followed the cookbook from like 5 slides ago, okay? I told you, right, the Hamilton-Jacobi-Bellman equation always looks like this. So discount rate times value function, then you have the period return function, derivative of the value function with respect to the state. This is just a dot here. And then you have the term capturing uncertainty here. I'm going to use here the notation minus j. Sorry, I think I probably also did that in the previous case. Minus j means just the other j, right? So if j equals 1, then minus j means 2. And if j equals 2, then minus j means 1. Okay. Now, because it's a heterogeneous agent model with a distribution, there's an additional equation. Okay, this additional equation is a law of motion for the distribution, and it's an equation called the Kolmogorov-Fourier equation or Fokker-Planck equation. Just by the way, if you ever hear Fokker-Planck equation, it's exactly the same thing as Kolmogorov-Fourier equation. Different people use different words for this, but it's the same thing. Okay. What does this Kolmogorov-Fourier equation look like? It looks like this. There's a 0 here. Why is there a 0 here? It's because it's the stationary Kolmogorov-Fourier equation. If you had a time-dependent equilibrium, like we just discussed, say if you had changes in the environment, there would be a partial G, partial T here, and then there would also be a partial V, partial T here. That was a question before. Okay, but here it's a stationary equilibrium, so there's a 0 here. Then there's a term here that captures what happens to the distribution because of saving. You can see it has the saving policy function enter here. I don't have super good intuition for this. I can show you a mathematical derivation for where this comes from. Don't have super good intuition for this. Then there's 2 more terms here. What are these other terms? So these other terms are, there's an outflow out of income state J, and there's an inflow into income state J. How does that work? Well, people flow out at rate lambda J, and how many of them are there? Well, a density of people, G of J at point A, okay? The inflow is sort of symmetric, okay? But the point is, in general, the Kolmogorov-Fourier equation is just an equation that keeps track of inflows and outflows of particular points in the state space that come from the optimal saving decision and the exogenous income process. Okay. There's a requirement distribution integrates to 1. And then finally, there's a market clearing condition. What's this market clearing condition? This market clearing condition just says that assets are in fixed supply. So for example, if B is equal 0, that would be the Huggett case where bonds are in 0 net supply. More generally, you could have that, assets are in some positive fixed supply, for example. Okay. Now the point is, all the equations you need to know for this, for characterizing this equilibrium here are essentially on the slide. So these 2 partial differential equations, the Hamilton-Jacobi-Bellman equation plus the Kolmogorov-Fourier equation, together with the equilibrium condition, fully characterize the stationary equilibrium. And what we're going to do later is we're going to talk about how to solve this on a computer. Okay. Okay. So let me move on. Now what we're going to do in the last 20 minutes or so is I'm going to show you first how to solve Hamilton-Jacobi-Bellman equations on a computer, and I'm going to, after that, show you how to solve a full heterogeneous agent model. And then hopefully, if there's time, which probably there isn't, to be honest, I'm going to do the case with these models with non-convexities. Okay. For all these numerical solution stuff, there's a lot of codes on my website. So, check those out and take a look. Okay. Here's the one slide summary of how to numerically solve Hamilton-Jacobi-Bauman equations. And I would say this is probably the most important slide of the entire lecture. So I'm going to kind of, go a little more slowly, and, I encourage you to kind of listen and concentrate for a second. The point is, once you understand kind of how this works, you're not only going to understand how to solve the Hamilton-Jacobi-Bauman equations, you're also going to understand how to solve the Kolmogorov-Ford equations. And in particular, you're going to then understand how to solve the entire models. Okay. And once you've sort of internalized, how to solve these differential equations essentially on a computer, then in particular where this stuff here comes from, you're going to understand essentially everything in the whole lecture. Okay. So here's the point, and it's going to be a bit high level and a bit abstract, but I just want to throw it at you, and then I'll spend essentially the rest of the lecture explaining this. Okay, so here's the question. Here's the point, right? We're trying to solve this type of a general Hamilton-Jacobi-Bauman equation. Here I did it for the deterministic case, but everything's going to be sort of analogous once you add uncertainty. So I'm not going to do that for now. And the question is how to solve it on a computer. Okay. What I'm going to tell you is we're going to discretize this equation. In particular, we're going to discretize the state. So we're going to put it on a grid. So X here is either capital in the neoclassical growth model or wealth in this type of a heterogeneous agent model. And then we're going to solve this Hamilton-Jacobi-Bauman equation using what's called the finite difference method. Now, what you can't see, there's no way of seeing this now, but what I'm going to spend the next few slides explaining, or the rest of the lecture really explaining, is that when you do that in a smart fashion, this finite difference method, then this equation here, which is a differential equation, and in general, say if X is a vector, is a partial differential equation with, say, I don't know, 5 state variables, okay, will collapse down to just a system of nonlinear equations that looks like this, where V is some vector and R is also some vector and A is a matrix. And this matrix is going to play the role of a transition matrix, and it's going to be really, really sparse. Okay. Now, two things. So first of all, what's the dimensionality of things? So essentially the way it's going to work is we're going to put X on a grid. So for example, if you have wealth and you put wealth on a grid with 1,000 grid points, and then say you have 2 income states, then the dimensionality of this vector V here is going to be a 2,000 dimensional vector. So 1,000 times 2. Okay. This matrix A here, the dimensionality of that is going to be 2,000 by 2,000. Okay, and in particular, it's going to just be a transition matrix that tells you how you move everywhere in the state space. Okay. The key thing that's going to happen, okay, is going to be that this matrix A in practice is going to be extremely sparse. And in particular, it's going to be tridiagonal. And I already said this in the introduction, and I'll explain it again in a second. Here's kind of what this is going to look like. So this is, in MATLAB, there's a command called SPY, S-P-Y. Okay, what does SPY do? SPY, if you type SPY A for a sparse matrix, then it produces a plot of the matrix where it puts white everywhere where there's a 0, and it puts blue wherever there's a non-zero. Okay. So the point here is there's only non-zeros either on the diagonal or one to the right of the diagonal or one to the left of the diagonal, which is what's called a tridiagonal matrix. Okay, what's the intuition? The intuition is exactly what I said in the introduction to the lecture, which is that what you're going to do once you discretize a continuous time process is you're either going to go one step to the right or you're going to go one step to the left. Okay, you're never going to go 10 steps to the right or 7 steps to the left. Okay, that's why it's going to have this nice sort of sparse tridiagonal structure. And then the whole point is solving this on a computer because of the sparsity is going to be super duper fast. Okay, so as I said, you have no way of knowing at this point how to go from there to there, and I'm going to tell you in the next few slides how to do that. But what you should be able to do is to see, hopefully, is that if you have a system like this, it's not that hard a problem to solve. Okay, whereas solving a differential equation, in particular partial differential equation, is maybe much harder. Okay, I'll skip this. Okay, I'll explain this just for simplicity in the context of a neoclassical growth model, just because it's sort of the simplest optimization problem that I think everyone's familiar with. But the point is going to be, it's going to generalize. It's going to generalize to the Bellman equation from the Huggett model, right? In particular with wealth and income. It's going to generalize to if you have 3 state variables. It's going to generalize to if you have 5 state variables. It's always going to look the same in terms of the structure. Whereas in contrast, just briefly, if you instead solved this type of an equation as a differential equation where you need a boundary condition, then once you go to more than 1 state variable, you're going to be in trouble, right? You're gonna, like, your numerical solution method is not going to work anymore. Numerical packages for solving PDEs are not very good in general. Instead, I'm going to give you an algorithm that's going to work, at least in principle, if you have multiple state variables and it doesn't matter exactly what the structure is there. Okay, there's some MATLAB codes also to solve this. And then, sorry, we're going to make some functional form assumptions just for concreteness. And again, so if you solve something on a computer, you better assume some functional form assumptions and make some numerical values for the parameter values. So that's what we're going to do there. Okay. Now, here comes this key thing. So this is our test problem again. So here comes the key thing. Okay, we're going to, again, I've already said this, approximate the Bellman equation with this kind of a finite difference scheme. Okay, what does that mean? So we're going to put the state on a grid. In particular, we're going to put capital here on a grid of capital I points. So let's say capital I equals 1,000, right? Then we have ki 1,000 ki values, okay? And we're going to approximate the value function at these 1,000 grid points. For now, let's also assume that the grid is equidistant. So you always have the same distance between all the points in the state space. That's not an assumption you need, and you can extend everything to non-equispace grids, but it makes the exposition a little easier. Okay. We're going to also use the shorthand notation v sub I to just mean the value function at the point I in the state space. Okay. Now, if you look at this, this all seems pretty straightforward. So you just put i's everywhere, but there's one term that's tricky, and which is this derivative here. So what do you do about this derivative? Okay. Now here's what we're going to do. We're going to approximate the derivative using what's called a finite difference approximation to a derivative. Okay, that's why the method has its name. Okay, that's why it's called a finite difference method. What is a finite difference approximation to a derivative? Essentially, the way to think about it is you're just kind of taking seriously the definition of a derivative. Okay, what's the definition of derivative? Well, definition of a derivative is you look a little bit to the right of the current point, and then you take the difference and you divide it by how much you look to the right, and then you take the limit as how much you look to the right. So delta k goes to 0. Here instead, we're just going to take sort of discrete counterpart to the derivative. Okay, so then let's just do this in terms of a graph. So how does this work? So you have capital on the x-axis, the value function on the y-axis. Ignore that it's downward sloping here. That's not going to happen. Okay, I took this from somewhere else. And then what we're going to do is we want to approximate the derivative at point I in the state space. Okay, And essentially, there's three ways of doing it. Either you take a backward difference approximation, that's this line here. You take a forward difference approximation, that's this line here, or you take a central difference approximation. Okay, here's the equations for this. You can convince yourself that, you know, this slope here is, for example, equal to that term here. Okay. Quick comment here, just because I took this graph from elsewhere. There's three possible, you know, finite difference approximation. There's also more. We're in practice only going to use either the backward or the forward difference approximation. We're not going to use the central, but you so kind of ignore that line if you want. Okay. Okay. Let me maybe pause like just for one or two questions in case there are any. Is it clear what we're doing?
I think you have one question here from Wei, who says, how do we solve a problem with an unbounded state space?
We assume that the state space is bounded, like we always do in economics, right? You put the problem on a compact interval, and then you want to just make sure that your upper and lower bounds of the state space are chosen large enough that you're not going to bump into them, essentially.
Thank you. I know this might be beyond the scope of this lecture. So for example, we have a wealth distribution where your wealth can have a Pareto tail or something, and your wealth can go to infinite.
Yes. Okay, fine. So yeah, yeah, it's beyond the scope of this. There's some notes on my website. If you look on my website, on the numerical algorithm summary, there's a section 8 or something, which is models with a fat-tailed wealth distribution, which is exactly what you have in mind. And then you have to put a boundary condition at the top, essentially, which kind of takes advantage of. So you put it on a state space, but you choose a boundary condition in a smart way to make sure that it kind of makes sense there.
Thank you.
Sure. Okay. So now let's do this finite difference approximation. Okay, so right, remember we're trying to approximate this Bellman equation, and I've said we put k on a grid, and we approximate the derivative with either the backward or the forward difference approximation. Okay, so now let's look at the equations for this. How does that work? So then the finite difference approximation to the HJB equation, one way of writing it is just like this. Okay, here nothing really happened. Okay, except that wherever there was a vk, I replaced it with v sub I. And then the other thing I did is I got rid of the max operator. So I maximized out by taking the first order condition. And I'm just saying consumption, right? Because the first order condition is u prime of c equals v prime of k. So consumption has to be the inverse of the marginal utility times the derivative of the derivative of the value function. Okay. Okay. So and then I'm also going to use the notation SI to denote saving at grid point I. Okay. So, and then the point is we're going to somehow solve this. And there's capital I of these equations. And what's going to happen, and that's going to be the point, is it's going to end up being this sort of a sparse matrix equation that I had a few slides ago. You still can't quite see that, but you can sort of maybe see how we're like moving in that direction. Okay. Now, I said here that VI prime is either the backward or the forward difference approximation. So meaning you're either going to use this approximation or this approximation to the derivative at this point in the state space. Okay. So, which one is it? Like, which one should you use? Okay. And where in the state space, so potentially you may want to use different ones at different points in the state space. Turns out this is extremely important, okay? And on the next slide, I'll show you what I think is sort of the best solution to do it. There's sort of a technical reason why this is extremely important, which is you satisfying this condition here, which is I talked about 3 slides ago that I skipped. But, try it out yourself. If you don't do this the way I did, or you do it the wrong way, essentially what's going to happen is your finite difference scheme is just going to spit out junk. So essentially what's going to happen is You're going to start iterating on the value function. At some point, you know, value function is going to become downward sloping. Then you're going to start getting imaginary numbers and, you know, crazy wiggles and everything. And the whole thing is just going to spit out junk. Okay. So it's very important that you do this in the correct way. So here's how to do this. And the key thing is we're going to use something that's called an upwind method or upwinding. Okay. Here's the basic idea, and this is sort of the best way of doing it. Okay. And you're going to see it's going to make a lot of economic sense as well. So here's the basic idea. Okay. The basic idea is we're just going to use a forward difference approximation whenever the drift of the state variable is positive, and we're going to use a backward difference approximation whenever the drift of the state variable is negative. Meaning we're just going to use the difference, the approximation in the direction in which we're moving. Okay, so meaning that if you're at point I here and you're moving up, well, then we're going to use the forward difference approximation. If you're at point I here and we're moving down, well, then we're going to use the backward difference approximation. Okay, right? This makes a ton of sense. You know, this is a forward-looking problem. So obviously you want to use the information in the direction you're moving. You're not going to want to use the information from the direction you're coming from or something like this. Okay. So given this, here's what the upwind version of the finite difference approximation from the previous slide is going to look like. Okay. It's going to look like, so these terms are just the same as before, but then we're just going to use this notation here. We're going to just look at savings, okay, and we're going to look is savings, right? Remember, savings is this thing here. We're going to look, is savings positive? Well, if it is, we're going to use the forward difference approximation. Okay, is saving negative? If it is, then we're going to use the backward difference approximation. What's the notation here? The notation here is I'm going to, for any number x, I'm going to denote by x plus, sort of the positive part of x. So SI plus here is the positive part of saving. Okay, so it's either 0 if saving is negative, or it's whatever saving is. And same for SI minus here, which is sort of the negative part of saving. Okay, this ignores two little complications. The first one is that if you just look at this, and the way I just said it, it kind of has a circular element to it. Why? Because saving itself depends on whether the forward or backward difference approximation is used. Why? Because saving depends on consumption, and consumption depends on the derivative of the value function from the first order condition. Okay, so like, you know, what am I talking about in a sense? Okay. The other thing that's sort of related is here it looks pretty similar, linear, but really it's a very nonlinear equation. Why? Because consumption depends on the derivative of the value function, again, through this first order condition here. Okay, and so we're going to in general need to iterate in sense somehow. Okay, what we're going to do is we're going to put these complications aside and then revisit them. In fact, I'm in this lecture, for the purpose of today, I'm just going to skip these complications. Okay, and there's some slides that I'm going to skip that explain how to handle this. Okay, so putting these complications aside, now we're almost there, and we're almost towards building up this sort of sparse matrix equation that we're going to want to solve. Okay, so here's how it works. So essentially, remember that here I'm just restating what was on the previous slide. We're going to want to you know, use the forward difference approximation when the savings are positive, and the backward difference approximation when the savings are negative. Now, if you just play around with this a bit, there's capital I of these equations, so 1,000 equations, say. You can see that you can write this in matrix notation. Okay, in particular, right here, I'm just restating that thing here by collecting this vector here, and then you have capital I of these equations. You can see that you can write the whole thing in matrix notation, where B is just a vector that has all the bi's collected in it, and U is just a vector that has all the U of ci's collected there. And then A, what's A? Well, A is a, say, 1,000 by 1,000 matrix if I is 1,000, which in particular looks as follows. Okay, what is this again? This is this MATLAB function SPI. Here's SPI. And what does SPI do? Again, it plots sparse matrices and puts zeros, it puts white, sorry, wherever there's zeros, and it puts blue wherever there's non-zeros. this is for the particular model that we're solving, in particular the neoclassical growth model. Okay, and you can see there's zeros everywhere except here on the diagonal, and then one to the right of the diagonal and one to the left of the diagonal. Okay, so why is that? Well, here's how this works. Okay, so first of all, what's this white dot here? Why is there, zeros everywhere in this row? Well, that's the steady state. Okay, if you're at the steady state of the neoclassical growth model, you're neither going to move up nor down. So you're just going to stay where you are. And so that's why there's zeros here in this sort of a transition matrix. What's the thing down here? Well, here at the bottom, you're moving up. Okay, so SI is positive. So you're going to use information of the value function going forward. You use a forward difference approximation. So that's why there's entries on the diagonal and one to the right of the diagonal. Okay. Here, instead, at the top of the state space, when capital is large, you're moving down. Okay. So that's why there's non-zero entries on the diagonal and one to the left of the diagonal. Okay. Here's another way of saying all of this. If you think a little bit deeper about what you're doing, okay. So capital really is a continuously moving state variable, right? So it's just capital, and it drifts up or down. But we put capital on a grid, and essentially what we're doing with this finite difference approximation is we're approximating the continuously moving process for capital with a discrete state Poisson process, so sort of like a lottery. And what this matrix A here, right, this matrix that pops up there, it does is essentially, it summarizes the Poisson intensities of moving around in the state space. And what you can convince yourself of is that this matrix has a very nice structure. Okay, in particular, all the diagonals are negative, all the off diagonals are positive. Why? Because all the diagonals are outflows, and all the off diagonals are inflows into the neighboring points in the state space. And then the other thing it has is all the rows sum to 0. Okay, why is that? That's the analog of how with a discrete time transition matrix, all the rows sum to 1. Okay, the property is that a continuous time transition matrix always has all the rows summing to 0, and here that's exactly what you recover. Furthermore, I've already said this matrix is tridiagonal and very sparse, so you can solve this very quickly. Okay, so that's kind of it. There's like these two complications that I'm going to skip. Okay, here skip. But essentially, just to remind you again, is what we're doing is we're taking this Bellman equation with a continuous state, and we're putting the continuous state on a grid, and we're approximating the derivative here with a finite difference method. When we do that, okay, we're essentially going to pick up this type of a transition matrix. What does this transition matrix do? Well, it kind of approximates with a Poisson process how you're moving around in the state space. Okay. Now, when you think about it like this, you can already see that this is much more general than just this neoclassical growth model that we're doing here. In particular, it doesn't matter if you have more than one state variables, multiple assets, non-convexities, and so on and so forth. Okay. So, okay, I'm gonna, I guess I was planning on sort of being about done now. I'm gonna take like another few minutes to actually get to what we wanted to solve, which is heterogeneous agent models, because we haven't done that yet, right? But before I do that, let me maybe very briefly pause and see if there's any questions here on the very basic ideas of like how to solve a continuous time Bellman equation here by discretizing the state space. Any questions? No? Okay. Good. So let's do computations for the heterogeneous agent model now. And the point is going to be, once you understand this, it's going to be like super straightforward. Okay. So here's how it's going to work. In the heterogeneous agent model, remember there's a Bellman equation and there's a law of motion for the distribution. So in continuous time, a continuous time Bellman equation or HAB equation, and a Kolmogorov-Ford equation. The way it's going to work is that the hard part is going to be how to solve the Hamilton-Jacobi-Bellman equation, and the easy part is going to be how to solve the Kolmogorov-Ford equation. This comes back to something I said in the introduction. It's sort of this two birds with one stone idea, which is that once you solve the HAB equation, you kind of get the Kolmogorov-Ford equation for free. And you'll see how it works. Now, the good news is we already know how to do the Hamilton-Jacobi-Bellman equation. And so we already know how to do the hard part. So I'm kind of going to go faster. Okay. Just as a reminder, here's the system we want to solve, right? So there's a Hamilton-Jacobi-Bellman equation. Then there's this new equation, Kolmogorov-Ford equation, and there's a market clearing condition. Okay. So here's the bird's eye overview of how this is going to work. Okay. We're going to use a finite difference method. When we use this finite difference method, we're going to, as before, discretize the state space. Let's put now wealth on a grid, and there's going to be some step sizes of delta A. Okay, so as exactly as before, we're either going to use a forward or a backward difference approximation. We're going to stack the vector, all the v's into a vector v, big or bold v, I guess, and we're going to do the same thing for the distribution. Okay, what's the dimensionality of these things now? Well, it's however many points you have in the state space. So in particular, say there's two income states, right? Say if there's 1,000 points for wealth in the state space, then V is going to be a 2,000 dimensional vector, and so is G. Okay. If you had 10 income points, so a more general income process, then you would have a 10,000 dimensional vector V and a 10,000 dimensional vector G. Okay. Now, here's what's going to happen. So the end product of the finite difference method is essentially, again, just going to be a very nice system of sparse matrix equations, where the first equation is going to look exactly like what we've already seen. Okay, there's going to be two new equations. This is going to be what's the discretized Kolmogorov-Ford equation, and this is just the market clearing condition, right? So the point is this, is this, this, is this, and this is this. Okay. And then the point is going to be it's easy to solve on a computer. The key thing, and that's going to be new for now, new, and I'm going to explain it if I have some time, is this matrix here that shows up in the discretized Kolmogorov-Ford equation. So this is the discretized Kolmogorov-Ford equation is just going to be the transpose of whatever that transition matrix is there. Okay, and I'll explain that in a slide or two. Okay. Now let's zoom in and just redo briefly how to solve the Bellman equation, and then do the Kolmogorov-Ford equation and the market clearing condition. Okay. This one, again, we kind of already know this. Yeah, I didn't even bother explaining it much more because we kind of already know how to do this. So as before, once you discretize the Hamilton-Jacobi-Bellman equation using a finite difference method, you're going to get the sparse matrix equation, where it's just now the dimensionality of the thing looks a little different. In particular, because there's two state variables, it's a little bit larger. Okay. What does this transition matrix look like now? It looks a little different than in the neoclassical growth model. Okay. In particular, this is again this function SPI here that tells you the sparsity structure of the transition matrix. It's gonna look a little similar. In particular, there's this sort of still this tri-diagonal structure here in the middle, but then you have also these off-diagonal things here. Why is that? Well, that's because you have these income shocks as well. Okay, so these terms here capture movements due to the income process. This is movements due to the wealth process. The way this works is this point here is the low income guys. This point here is the high income guys. If you remember the saving policy functions, so these blue and red lines, I should have put them on the next slide maybe. You can see that all the low income guys, they're decumulating wealth, so they're moving downwards. Whereas for the high income guys, some of them are accumulating wealth, so there's entries above the diagonal, and some others are decumulating wealth. there's some entries below the diagonal. Okay. What's this point here? This point is where the saving policy functions of the rich guys intersect 0. Okay, where you switch from accumulating wealth to decumulating wealth. So this is what captures precautionary savings, and this is just people decumulating wealth. Okay. Now, just very briefly for the Kolmogorov-Ford equation. Here's the equations you want to discretize. Okay, it's essentially these two equations for the distribution. How do you do that? You may be tempted to sort of work through this and try to do a finite difference approximation to this. You can do that, and if you do it correctly, it's gonna work, and you're gonna get the correct answer. But you actually don't even have to do that. Instead, there's sort of a shortcut, which is you just say, oh, wait a minute, shouldn't it have something to do with the transition matrix of the process? Okay. In particular, turns out that if you discretize this equation here in the correct way, remember this matrix A here, right? That we just looked at. That's in the Bellman equation. That's exactly shows up again in the equation for the stationary distribution. And the equation you just have is 0 is equal to the transpose of the transition matrix times the distribution. And then you have to find the G that satisfies this. If you are familiar with these kind of models, you'll see this is an eigenvalue problem. Okay. In particular, it's really lambda times G equals A transpose times G, where lambda is equal to 0. So you're finding the eigenvector corresponding to a 0 eigenvalue. Okay. Now, if you know your discrete time Markov processes, what this should remind you of is the problem of finding a stationary distribution in a discrete time Markov chain. What do you do there? Well, you find the eigenvector corresponding to a unit eigenvalue. Okay. Here, what you do is you find the eigenvector corresponding to a 0 eigenvector. Okay. Why is that? Well, it's just because essentially everything that's a 1 in discrete time is a 0 in continuous time. That's like kind of the rough idea of how to remember it. Right? The period length is 1 in discrete time, 0 in continuous time. Okay.
And we should wrap up so we have a little bit of time for questions at the end.
Yes, I'm exactly done. Okay, there's a way to iterate on the equilibrium interest rate. And then what I don't have time to talk about, but I'm happy to take some questions on in the Q&A, is these models with non-convexities. Once you understand what we've done so far, it should be pretty straightforward to figure out how to do this. The reason I put this there is because this is something that comes up in macro development applications. And I think is sort of lots of very interesting problems have these non-convexities, again, occupational choice, these S-shaped production functions. This is something where these continuous time methods really shine and make your life a lot easier. As you can see in particular, say if you play around with these codes from Joe's paper that I have here. Okay, so let's pause and take some questions.
If I could ask?
Yeah.
Regarding the non-convexities, are the first order conditions in continuous time sufficient? Because I was reading your paper and I'm not completely sure about whether I get it correctly. So is it that the first order condition is sufficient, or the upwinding scheme is enforcing this?
Right. So yeah, let me maybe briefly do it for everyone. Okay. So the type of problem I have in mind is a problem where, say, there's a fixed cost in production, or you choose between two different technologies. So sometimes people call this a butterfly technology, right? So there's a crappy technology that you can use, or you can pay a fixed cost, and then you can use the better technology, and then your effective production function is sort of the upper envelope of this. Or an occupational choice would be like this. Now, what happens in discrete time is that the value function, or that happens both in discrete time and continuous time, the value function will inherit this non-convexity. Okay, it's going to have a convex kink at some point in general. Okay. Now, what happens in discrete time, it messes up your first order conditions. particular, as exactly Jan just said, the first order conditions are no longer sufficient, and you typically have multiple solutions. Then there's ways around this using lotteries and so on, but those are kind of typically complicated. Instead, what happens in continuous time is it's much, much simpler, and it's exactly what you're saying, which is that the first order conditions are just going to be sufficient. And the reason is, do I have it here? I don't have it here. The reason is that the first order condition, so if you look at the first order condition of this, the first order condition here is just going to be u prime of c equals v prime of k, okay? And it doesn't matter whether the v has a kink or not, okay? Because given a guess for the value function, v prime of k is just a number. And so you can say if it's CRA utility, you just do c is equal to v prime of k to the minus 1 over gamma, and you're done. And you just don't have this problem here that you have in discrete time, that you have these insufficient first order conditions.
So this holds generally.
Yes.
Nice.
And the intuition is that it comes back to this tomorrow is today thing, right? Which is that what happens in discrete time and what messes you up is that you have to sort of worry when you make your saving decision. You have to worry about crossing the non-convexity between today and tomorrow, right? Because it's like, if I do one thing, then I cross the non-convexity, and if I do another thing, then I don't, and then, well, in which case, okay. In continuous time, you just don't have to worry about that, because you only have to worry about what happens in an instant of time, and what's relevant there is just the value function at that point in time. Okay. There's some more discussion in this Ashtu et al. Paper that I refer to. Okay. Yeah, sorry, Selena.
Yeah. Sorry, I have a very naive question on how we could use continuous time methods if we had age involved. So if we had some OLG structure in there.
Right. It's pretty, so, but your question is just how would you solve a model with age? Is that?
Yes, basically, like if you could just explain where to start with that.
Yes. Okay, so there's a code on my website. With some, if you look at my website, it's something called like lifecycle.m or PDF. Okay, and it's very simple, really. So essentially, age is just another state variable, and if you have, and age is just a state variable that has a drift of 1. So age dot is equal to 1, because for each time unit that passes, you accumulate 1 more year of age. That's just how it works. Okay, and so yeah, you just if you say wanted to solve a model with overlapping generations where you have an age structure, then you would just have an extra state variable. Distribution would be say you take the Ayagari model I had or the Huggett model I had, and you introduce age on top of wealth and income. Then rather than having 2 state variables, you just have 3 state variables, and age would be an additional state variable, and you would have a joint distribution of wealth, income, and age, and you just have to track that bigger dimensional object. And maybe you'd want to have some death probabilities that depend on how old you are, right? You can do that simply with a Poisson process that depends on age, and that's just kind of what you do. If you email me, there's some students whose theses I co-advised who wrote this up in a nice way, and I can send that to you.
Thank you very much.
Sure.
Then we have 2 questions from the Q&A.
Yeah.
2 very good questions. Samuel Marshall, could you possibly discuss if there are any issues with using continuous time methods for discrete data? And then Hee-Jong Kim, is the solution method stable if you have a large shock that changes the distribution a lot? It looks like the solution method relies on the fact that everything changes smoothly.
Right. Okay. So yeah, both very different questions. Obviously, both great questions. I agree. So the way to think about the issue, whether there's any problem or not with applying continuous time models to a world where you observe data at discrete time intervals as follows. So, okay, first of all, just as background, yeah, obviously it's true that typically data we observe at discrete time intervals, okay? So like survey data are, collected every year, or, the national income and product accounts are, computed every quarter. And then, so how do you do that? So the answer, I think, is really quite simple. And it comes down to realizing that also in the real world, really time is continuous, okay? Right? Obviously, time is continuous. It's just the data that's observed is at discrete time intervals. So what do you want to do, say if you have yearly consumption data, is you just want to solve it in continuous time and then just time aggregate your consumption flow over a year. And all you have to do is essentially just be a little bit careful about these kind of time aggregation issues. Whereas with a discrete time model, you're just kind of assuming that people only make a decision once a year, and then you don't have these kind of issues. And that's essentially how you do that. There's some discussion in the paper with Ashtu and these other people about, for example, how to compute marginal propensities to consume over a quarter in this kind of a model, which is what you typically see in the data. And that's exactly the type of thing then you're going to have to do is sort of time aggregation. Okay. Yeah, I'll stop there. We can discuss this more later if there's a follow-up question maybe. Other question, which was, what happens if there's a large shock that moves the distribution? No, I don't think that's an issue at all. It's gonna, at least not in principle. What it means is that it's gonna be harder to solve the model because you're gonna have to maybe let the distribution move around over a larger state space. But so, for example, you could have, and I have some codes I think somewhere on the website. So you could have a shock whereby in an Iagari model, whereby just half of everyone's wealth gets destroyed. Okay, so a huge negative shock to the distribution, and then you can just compute the transition dynamics after that shock, and that works perfectly fine. And there's like nothing like problematic with that.
Actually, I mean, the what it relies on is the fact that time is smooth, not that the distributions are smooth. And in fact, it seems that it's going to be, the continuous time methods are going to be more helpful I think, in a situation where you have a big shock because of what you explained about the mass points, which is getting one big mass point isn't going to lead to a bunch of echoes of these mass points later on from the big shock.
Yeah,
that's my guess. I don't know.
Yeah, no, that's a very good point, actually. Thanks.
Well, I guess we are out of time, and I want to thank Ben for a tremendous lecture and a tremendous generosity to do this. We put a lot of effort into this. If we can unmute and give Ben a round of applause. And then I want to thank Doug for moderating the first half. I accidentally moderated the second half. And we thank again Mandy Chan and Lauren Waring and Kirsty McNeil at CEPR for the logistics to make this all possible. Next week, we will have Yong Xin, who will be giving us some applications to this. I mean, it relates to these methods of heterogeneous agents relate to, incomplete markets, frictions that are in the world that are common in developing countries. So Yong's will give us a couple applications. And of course, the things that Mushfiq talked about are also relevant. So we hope to see you there next week. Thanks again, Ben.
Thank you very much. And I encourage you to go to Kotya's TA session on Monday. So again, where I realized I went very fast. So,
Do you want to mention what he'll cover, or have you already done?
Yeah, I did it in the beginning very briefly. He'll essentially go through some of these codes, in particular, the codes for solving these problems with non-convexities that I didn't have time to cover. So I think that'll be kind of useful. And just the code for solving the basic heterogeneous agent model, essentially.
Great, thanks. Okay, see you all next week.
Thanks, guys.
Thanks, Ben.